Good evening, everyone. My name is Jyoti Sharma, and this is week 8. Live session will be from 6 to 8 p.m. This is brief introduction that right now I'm a PhD student from ISA Bhopal. I did my undergraduation in botany honors and post graduation in environment management from FRI Dehradun, and I already have taken some NPTEL courses. So I have experience of taking these three courses: air pollution and control, environment chemistry and microbiology, basic environment engineering, and pollution abatement. This is how it will help me to make you understand about this subject also, because this is uh, similar to the NPTEL courses that I already have taken. And how we will proceed, this is just like from week 1 to till week 7, that I have a lot of MCQ questions, and you people are encouraged to speak, to communicate, and to discuss what should be the right answer out of this four option. And please don't worry if you are giving me wrong or right answer, because I'm here just to correct you. Your participation is highly valued. Here is just the brief that what we already have learned, and at what position we are right now, and we will learn what we will learn in future. This is just the brief. First we started with the environment compartment. So this week was related to the environment compartment and where pollutant may be present, right? So for example, we have air, we have water, we have soil. So where the pollutant may be present, we learned about different environment compartment that we have. Then we also discuss about if if water have some a discrepancy, or if the air is pollutant, then what are the different parameters that we should learn about. So we talked about water quality and screening parameter, we talked about the air quality parameter. But as I told you, because we are interested to see what is the concentration of our pollutant and where is it, either it is in water or soil or in air. So for that, it was necessary for us to learn about soil air partition coefficient, uh, air water partition coefficient, and a lot. Like, we have different compartments, so we learned about different partition coefficient, and we learned that what is the affinity of a particular component or particular pollutant to be at that compartment. So it is just about that affinity or tendency to be there. It is something like that. If we do have benzene, so benzene is organic in nature, so benzene will like to be in organic solvent, right? And if we have any organic solvent, then yeah, the partition coefficient will be higher in that case, as comparison to the another compartment where we do have, let's say, inorganic things, right? So we learned about this partition coefficient. That was very important, and till now we are making use of this partition coefficient. In week 3 we started with environment analysis, and because this course is all about environment monitoring and sampling, so it was necessary for us to understand how we can do the monitor and what precautions we should need to take. And so we learned about making the standards and about the precision accuracy of the instrument, and also we learned of this in week 3. In week 4 we started with the analysis procedure that we can have for organic in water, as I gave you the example of benzene. So if we do have benzene in the water, then how we can measure that concentration. And it was just like that, for the instrument to measure it, the concentration should be highly concentrated, and that's how we have to extract it to different solvent, and the property of that solvent should match to your organic, right? That's how it we can extract it from the water, and then we can concentrate it using evaporation, and we do have a lot of method that we discussed, and that's how we can use this concentrated organic to the um, instrument, and that's how we can measure it. So we learned this in week 4. In week 5 also we proceed with the same thing, but we learned more about chromatography and mass spectrometry. In chromatography we learned about gas chromatography, liquid chromatography, and even HPLC. uh, Mass chromatography we learned little bit, but yeah, we touched. uh, then we talked about again different so till now it was organic in water, and we also saw how we can measure if we do have particulate matter in the air, or how we can measure the microorganism in the water, or let's say in the air. So we tried to see different methods to measure it. So this was till week 6. But the little bit we move forward to the air, and monitoring the concentration of pollutant in the air is very complex, because it is moving, right? And it is very uncertain. We have weather, and if let's say we have turbulence, or there may be rain. So just to get the concentration uh, per time, and even at particular space, it involves a lot of things. It involves the thermodynamics, and it involves the fluid flow. So that's how this is very complex. But we started with the box model in the last week. uh, so how we can use this box model in the water, box model in the air, that's how we can estimate the change in mass per time. So we learned about these things. We touched the lapse rate, mixing height, and plume behavior. But yeah, the fourth lecture, I do have 5 or 6 more MCQ question on it. So we will try to solve that also. And because this is week 8, so this week 8 is all about Gaussian dispersion model. Then what different parameters we have in that dispersion model. We will talk about it in lecture 2 and 3, and then again Gaussian dispersion model, different example, and additional topic we may have. So yeah, so today our focus will be more on the air, and because air is moving up. Here the dispersion model, I'm just giving you the quick introduction, that if we do have a chimney, and so we can call it as a stack, and from the stack you have the plume, right? You have the smoke coming out of the chimney. So and chimney, that plume that we have will have a lot of contaminant, will have a lot of pollutant, and we need to measure it. But you have to see the wind is also moving, right? And you have to see what is the velocity, and what is the temperature at which it is moving, and even the temperature of the plume that we have. Based on that only we can estimate with some uncertainty that okay, at that at that particular location the concentration may be this and that. So so this is how we will start with the estimation of the concentration, or estimation of the mass of any pollutant with the changing time in the air. So yeah, let's start with week 7, last lecture that we didn't cover in the last week, and then we will go to this week 8 content. Okay. So my first question is, if we do have a plume, right, and plume is releasing from the stack at 50 degrees Celsius when ambient air is 30 degrees Celsius, if the parcel rises 500 meter, estimates its temperature assuming dry adiabatic cooling. So let me tell you what this question is asking or demanding from you. So this is our chimney, right? And so it is, there is a plume that is coming out of the chimney, and that already have the temperature, and that temperature is 50 degrees Celsius, right? But what we learned is that we have air, but air temperature is little different from it, and this is 30 degrees Celsius. So if let's say if this is our parcel, right, if this is our parcel, and if this parcel is rising 500 meter more, then what its temperature, assuming that it is the dry adiabatic cooling. So you have to tell me the temperature of the plume that we will have if that plume will rise 500 meter. So obviously we learned about the lapse rate, right? If we will rise something, then temperature will be cooled down. Okay. And you have to see, but at what rate it should be cooled down, right? So if it is a dry adiabatic cooling, so what does that mean? It means that this is, let's say, our temperature, and this is your altitude, or you can say the elevation, and this is how your temperature is reducing with the increasing in the elevation. If it is the dry adiabatic cooling, so dry adiabatic cooling means the rate is something 9.8 degrees Celsius per kilometer cooling. So you can say per kilometer there is a cooling of 9.8 degrees Celsius. And because our plume, our air parts, our parcel is rising 500 meter only, so it is something like that 1000 meter rising is giving you the cooling of 9.8 degrees Celsius, right? 500 meter rise will give you the half of this cooling, right? And half of this is 9.8 divided by 2, and this will be 4.9. The cooling of 4.9 degrees Celsius, and this is per 500 meter. Okay, and initially your temperature was 50, right? But if we are rising it, then it will lose 4.9 degrees Celsius, and that's how. So this is 50 minus 4.9 degrees Celsius, and this will be something 45.1, right? So what we learned is that if we have plume, that plume have temperature 50 degrees Celsius, but we know that there is a cooling governed by a dry adiabatic. It means whenever we are rising it, there will be the cooling of 9.8 degrees Celsius per kilometer. But in the question, it is that we are rising just 500 meter. So it means that we have to divide it. Okay, so if we are dividing it by 2, then this means there is the cooling of 4.9 degrees Celsius, and if we are subtracting it 50 minus 4.9, then this will give us the temperature of your parcel will be 45.1 degrees Celsius. So this is how we can calculate using the lapse rate the temperature that we will have of our air parcel that is coming from the chimney. So the right answer will be 45.1 degrees Celsius. Okay, I already have given the explanation, so I'm skipping it. Okay, so the next question is, if environmental temperature at ground is 30 degrees Celsius and at 1 kilometer height is 25 degrees Celsius, what will be your environmental lapse rate? So I have four option: minus 5 degrees Celsius per kilometer, minus 9.8 degrees Celsius per kilometer, minus 2 degrees Celsius per kilometer, and plus 5 degrees Celsius per kilometer. So this is something that you have this is your elevation, this is your temperature, and what you learned is that let's say your temperature here is 30 degrees Celsius, and at 1 kilometer height, so let's say this is 1 kilometer height, so at 1 kilometer height the temperature is 25 degrees Celsius. So the question is, what is your ELR, environment lapse rate? What will be your environment lapse rate in such condition? At ground, it is 30 degrees Celsius. At 1 kilometer, it is 25 degrees Celsius. And based on that, what will be your environmental lapse rate? I think this is very simple, because whenever so lapse rate is nothing but the decrement in the temperature with the elevation, and we are finding it per kilometer, right? Per kilometer, how much cooling it is inducing, right? So if we had 30 degrees Celsius at the ground, but at 1 kilometer it is 25 degrees Celsius, it means there is a cooling of 5 degrees Celsius per kilometer. And because if it is a cooling, then we are inserting minus sign here. So that's how A will give you the right answer. So this is your environment lapse rate in such condition. And it is worth to mention that your environment lapse rate changes with time, with space, with season, with the year. So this is the variable that is changing at each moment, right? This is not constant. If you have We already have learned about DALR, that is dry adiabatic lapse rate. This will be 9.8 in any of the condition, because this is something ideal condition and we calculated it from ideal gas equation only. So your dry adiabatic lapse rate will be constant, that is 9.8, but your environmental lapse rate will be changing with changing in the time dimension or space dimension or season dimension, such like that. So A is giving you the right answer for this. Okay, so coming to the next question, and this is, if mixing height increases, so if mixing height is increases from 500 meter to 2000 meter, pollutant concentration in the air box will generally, and we have four option here: increase 4 times, remain constant, decreases, increases slightly. If we are increasing our mixing height, initially mixing height was just 500 meter, but if we are increasing our mixing height, that is 2000 meter, then what will happen to the pollutant concentration? Will it increase, will it decrease, it will increase over time, or what will happen to it? So this is something like that. Let me give you. So this is, let's say, ground, and this is, let's say, your stack. again the chimney, and out of the chimney you have some pollutant that is coming, right? So let's say you're mixing so let's say this is let's say this is 500, and so this was your mixing height. And what if we will increase your mixing height to the 2000 meter? So this is something. So mixing height is where your gases will mix together, and that's how mixing height will always give you the less concentration of your pollutant, because it will mix the things, right? And that's how it will not accumulate the pollutant. So if it was 500 meter, it means within this area only your pollutant will be present in this area only. But if you are increasing your mixing height, it means your pollutant will be mixed in these areas, right? And that's how, if we are increasing the area, the density will reduce, right? Per meter cube of the air, per meter cube of the air, your concentration will be your mass will be reduced. So that's how we can say the concentration will reduce. So yeah, C is the right answer. And mixing height relation with the pollutant concentration is not very linearly. So we can't say 4 times or 6 times, not like that. And it is not increasing, it is decreasing. So this is not the right answer. Constant is also not the right answer, increment is not the right answer. So yeah, uh, whenever we are increasing the mixing height, pollutant will mix and mix in a large area, and that's how concentration will be reduced. So C answer is the right one. Okay, so the next question is, if we have emission rate that is 200 kg per hour into the above air box, and wind ventilation rate is 5 into 10 raised to power 8 meter cube per hour, steady concentration increase is. So this is something, again I'm drawing that stick, and if the emission rate, so this is, let's say, E, so how much it is emitting. So our pollutant is emitting something like that, 200 kg per hour. But your wind ventilation rate is up. So because this is the air box model, so this is something that this is the box model, or here I can draw. But your wind ventilation rate is, so wind is removing it 5 into 10 raised to power 8 meter cube. But so this is not the concentration, but this is how much air is getting ventilated out of this box per hour. And then you need to calculate the steady concentration increase. So the formula is very simple here. So it is giving the emission rate, how much is emitting of the pollutant, and the wind ventilation rate, how much wind can go out of this box. Based on that, you have to tell me the steady concentration. Steady concentration means in and out will be equilibrium. So here is just a simple formula that we have, is the, to calculate the concentration, the formula is just the emission by flow. And already we have the emission 200 divided by flow, that is 5 into 10 raised to power 8, and that's how the value will be 0.4 mg per meter cube. So yeah, this is very simple formula that you can apply to solve such kind of question. Okay, so the next question is, if we have a stick, and stick is releasing the pollutant, and the temperature is 100 degrees Celsius into the ambient air, that ambient air have the temperature of 20 degrees Celsius. If parcel rises 1 kilometer, parcel temperature becomes approximately what? So this is something that if we have a parcel, so let me again build up, just 1 minute. So this is something that we have a stack again, and stack is giving you the plume. This is plume that you have, and plume have temperature of 100 degrees Celsius. But here the temperature in the environment is 20 degrees Celsius. And if your air parcel rises 1 kilometer, so if it is rising 1 kilometer, what will be the temperature? So here what we are assuming is that this 20 degrees Celsius is at 1 kilometer. So for the next 1 kilometer, there will be the decrement in this. So what we are assuming here is that, let me show you the answer first. So, okay, I don't have the answer for this, but let me explain it. So this is something that we assuming here, that at 1 kilometer, there is temperature of your environment is 20 degrees Celsius. I know this question is not giving you the full information. So that's how there is the assumption that at 1 kilometer, there is a 20 degrees Celsius temperature in the environment. And that's how when it will, uh, here the environment lapse rate is 20 degrees Celsius, minus 20 degrees Celsius. So initially your stack had the temperature that is 100 degrees Celsius. So if it will rise to 1 kilometer, then it will reduce the temperature by 20 degrees Celsius. And that's how this will give me approximately 80.2 degrees Celsius at 1 kilometer. So that's how this question was solved. So this question was solved based on some assumption. Okay, now we are moving to the Gaussian model, and this is, yeah, this is about the week 8. So yeah, I have a lot of questions related to this. So in the Gaussian plume model, we have coordinates, that is y node and x node, that represent what? Source strength and wind speed, receptor coordinates of minimum concentration, coordinate where concentration is maximum, reflection points at the ground. So because I'm just talking right now about this coordinate y node and x node, but the first thing that you need to learn is what is this Gaussian plume model, right? So I think if you will give me the answer, then yeah, I will discuss a little bit about this Gaussian plume model, and then what these coordinates represent. So here, Um, okay, first you have to understand what is Gaussian plume model, and second is what are these coordinates, y and z. But here we are talking about the y node and x node. So let me draw this again because this is all about the chimneys and the plume. So let's say this is your plume that you are having, and so what we assume is that, so this is, let's say, your center line, Okay, so what we can see is that if you have a plume and if your plume is going in the x direction, this is your x direction, this is your z direction, and this is your y direction. Okay, so if your plume is going in the x direction, the plume may spread, right? Plume may spread vertical and horizontal also. Okay, so plume will spread in the y direction and in the x direction. So here y node and x node is something talking about the center line. What I'm saying is that for example, if you had that plume and that plume spreaded 10 kilometer in the y direction and let's say 2 kilometers. So what I'm saying is that this is something your center line and this is your x spread. So sorry, jet spread that you have, let's say this is 2 kilometers spread vertical and 2 kilometers spread downward. Okay, so this is your spread in the y direction. In the x direction there is the spread in the horizontal also. So in the horizontal, let me draw such kind of things. So there is a spread. So let's say this is the spread of 1 kilometer, and here is also spread of 1 kilometer. So what we are talking about, we have a center line. Center line will have the maximum pollutant concentration, and there is a spread vertical and the horizontal, and that's how if we do have the center line, in the center line the value of this z and y will be z node and y node. Okay, and because as and you know the Gaussian model, right? So this is normal distribution things. So uh, the maximum thing will happen near to this center point, and then there is a decrement whenever we are moving toward the tails, right? And that's how if we are near to the center line, your pollutant concentration will be higher. But as you will move away from it, your concentration will be reduced. And there is a spread that we have out of this plume. So what we learn from it is that these are the coordinate where concentration is maximum, right? And I think my next slide is giving you a brief introduction about this Gaussian plume model. So let's see just it is very important to know what this Gaussian plume model is. So this is nothing but the mathematical model that we will use to predict how your air pollutant disperse in the atmosphere. This is very important. How your air pollutant is dispersing in the atmosphere from a continuous source, for example chimney or the stack. So and because I told you, if your plume is something like this only, it means it is very uniformly increases, the spread is increasing very uniformly. So this will come under this Gaussian plume model or the Gaussian distribution that we have. And crosswind vertical direction and while being transporting downward to the x direction by the wind. So um, we will talk about the derivation also because this is very important to understand. But after derivation, what we will learn that if we want to calculate concentration at x and y and z coordinate, so this will be directly proportional to your flow rate. This is q by 2 pi. This is your wind velocity. So whenever we will have more velocity, this will give you the less concentration because it will help you for the dispersion, right? So that's why this is inversely proportional. And then the dispersion in the x direction, sorry, dispersion in the y direction and dispersion in the x direction. So this is the spread. If we will have more spread, it means it will give you the less concentration. So that's how this is also inversely proportional. Okay, and then there is some expansion of this y square upon, so this is your spread in the y direction, this is your spread in x direction. And we will talk about these things, but just giving you the brief idea how we can calculate the concentration at a particular location in x, y, z coordinates. This is, I think you already have learned about this, but from this only we are calculating or we are deriving the things. Um, you just need to remember few terminologies. For example, we have three coordinates. Already we know that. We have x coordinate, we have y coordinate, and in the y we have minus y and plus y, because your spread will be horizontal in that direction and in this direction also, right? And that's how we have minus y and plus y. In the z, we because we do have ground, right? So that's how this is just unidirection, it is not the bidirectional. So we have z. The chimney height is your hs. This is actual stack height. Then your plume will rise, right? Your plume will rise this much. So this is your del h. So if we will sum up this del h plus hs, so something like this. So this will give you the effective stack height. And as I told you, there is a spread in the y direction, so and there is the spread in x direction, z direction. So that we need to learn, because a lot of question will be based on these terminology only. And yeah uh, so after all, what equation we will have will be like this. And we already have learned about this pollutant concentration. This is pollutant concentration, your emission rate, q, your wind speed, this is u. These are your spreads, horizontal dispersion and vertical dispersion. And you have distance in the y direction, in the z direction, and in the x direction. So this is your downwind distance, crosswind distance, and height at receptor. And effective stack height, we already have learned about this. So this is the final equation that we have. And but before that, we have a lot of derivation that we will try to solve in the, I think, after a few minutes. Okay, so coming to the next question, because I already have given you the description about Gaussian plume model. So what will be the dimension of this rho y and rho z? M by T, L by T, L dimensionless. What will be the dimension? What will be the unit of your rho y and rho x? Or sorry, this is not rho, but this is sigma, sigma y and sigma z. What should be the dimension? So this is spread, right? And if it is a spread, then what should be the unit for it? So what I told you that we have the center line, and from center line it is spreading in the y direction, to the positive side and to the negative side. And it is also spreading to some height, so to some z direction, right? So if it is talking about the distance, the spread, so the unit should be, yeah, so unit should be the length unit. So this is, let's, so this is something, again I'm drawing the same thing. So this is your plume and this is your center line. So how much is spreading, right? These are just the dispersion, crosswind, and dispersion in the z direction. So if it is a dispersion at and dispersion is giving you the distance, to what distance it has been dispersed from that center line, so this will give you the length. So the dimension of this sigma y and sigma z are nothing but the length. uh, Let me give you so yeah, We were here, right? We were here. Just see this. uh you have this y is nothing but your crosswind distance. So distance means your length, and it is the square of the length. It is a square of the length. And below that you do have uh, 2 sigma square. So this sigma is again the horizontal dispersion, so this is again the L square, right? So here the unit are same. This will be cross, and this will give you just one value. And likewise, just here, see, this is height. So height is giving you the length, and the length square will give you the length square, and this is again the length square. So these are something that you can understand. Okay, coming to the next question. If we are estimating SO2 concentration at ground level, and ground level but 50-meter crosswind and 500-meter from the stack implies the receptor coordinator. So you have to tell me the receptor coordinator. So let's say you have chimney, and chimney is again giving you the SO2, and you have a receptor here, and so the chimney is giving you some SO2 concentration to here, and you want to know the receptor coordinate here. So this coordinate will be XYZ. So you have to tell me what are the coordinate for the receptor in that condition if we want to estimate SO2 concentration at the ground level, 50-meter crosswind and 500-meter from stack. Yeah. So yeah, C is the right answer, because we want to see 500-meter from the stack. So this is your stack, and we want to calculate here. This is, let's say, 500-meter. And because so your X will be 500-meter. We have crosswind 50-meter, so we are not going directly to the center line, but there is a spread, and we want to go to 50-meter away from this. So this is your 50-meter, and because it is at the ground level, so ground level means your Z, that the height is 0. So this is how this will give me the C answer, the right one. Okay. So let's say you have a line, and in line you have multiple stacks. So let's say there is the one stack, there is a second stack, there is a third stack, and every stack is giving me some plume, right? So, and the center line concentration factor is approximately proportional to what? N. So N is the number of stack. N is number of stacks. So your concentration will be proportional to what? Directly proportional to the number of stack that we have. N raised to power 1 by 2, n raised to power 4 by 5, n square. So you have multiple stack in the line, and each one is giving you some center line concentration. So if you want to estimate, let's say here, or let's say here, and this place is the receptor for all of these 3 stack concentration. So your concentration will be dependent on, obviously will depend on the number of stack, but in what way? Directly, just directly proportional to n, or n raised to power 1 by 2, n raised to power 4 by 5, or n square. So this is here the answer is n 4 by 5, and 4 by 5. So this is something that initially what was estimated that this should be proportional to n. So how many stacks we have, this should give us the center line concentration factor. But this was not the case, because when a lot of experiments and a lot of research were done, then they people analyzed that this is not directly proportional to the number of stack we have, but there is an empirical relation that we have, and this empirical relation is saying that this concentration factor will be proportional to the number of stack raised to power 4 by 5. So this is like they had multiple stacks, and then there is the concentration that the people estimated, and then they tried to estimate into that equation what would be the equation with the number of stacks, and then they found that more appropriate relation between number of stack and the center line concentration factor will be when we have number of stack raised to power 4 by 5. So that's how it was decided, and yeah, we are following it. So C answer is the right one. So whenever you have multiple stack that are arranged in the line, so it should be like the constant total concentration should be and multiply by a single stack concentration. But this is not the case, because plume interact and mix with each other, right? And because of that, there is some diffusion, there is the plume merging, there may be vertical or lateral spreading, there is the wind shear, and that's how not all pollutant mass from every stack reaches the center line receptor location. So this is slightly lesser than the linear, and that's how this is raised to power 4 by 5. Okay, coming to the next question. Among the regulatory model that we already have shown, the one identified as a puff model that can represent a continuous plume as a series of puff is ISC3, air mode, CalPuff, AP42. So this is something that, again, we have the chimney, and chimney is giving you some plume. So let's say it is giving you the plume, and plume, it is giving you the puff. So whenever we are calculating the concentration of your pollutant, when we are considering a puff, we are not considering the box model, but we are here we are considering a puff, and for the puff we are calculating the concentration. So if this is the case, then what kind of model is using this puff thing? So right now we do have a lot of models that can give you the concentration of pollutant, and for example, just giving you the example, like for texting or for messages, you have a lot of apps, right? You have WhatsApp, you have Telegram, you have uh, Hike or whatever. So you have a lot of messenger. So likewise, if we want to calculate uh, how our pollutant is transporting in the atmosphere, in the air, then we do have a lot of model, but the concept of the model may be different. So in the model where we are considering that plume in the form of puff, and then we are calculating this concentration of the pollutant and how it is changing, how the mass is changing per time, then the model name is CalPuff. So the C answer is the right one, because in ISC3 and in air mode we are having this box model, but in CalPuff what we are considering is the puff, and we are calculating everything for each of these puff, and then we are integrating it. So C answer is the right one. So this is something that I wanted to show you. that we have a plume. This is plume, and this is the wind direction. So whenever we are moving away from the stack, then your puff will increase in the size. And if we are calculating everything inside that puff, then that model that we use for such concept with such concept is calpuff. Okay. So the next question is, we have reflected plume term in the Gaussian dispersion equation that has been introduced mainly to account for chemical reaction in air, wind shear at stack height, ground reflection of plume mass, crosswind compensation. So you have one term that is the reflected plume, and we already have talked about this Gaussian dispersion equation, but we can add within that dispersion equation, we can add reflected plume term. So what does that mean? What it will reflect to us? So yeah, the C answer is the right one. This is the ground reflection of plume mass. Let me tell you how. So let's say you have again stack, and the stack is giving me uh, there is the dispersion, and let's say this is your height, right? This is your ground level. This is your ground level. So it means that there is a pollutant here, there is a pollutant here, and then because we do have the ground, then this pollutant concentration or this pollutant mass that we have will not go into the ground, right? Will be reflected back, will be reflected back. Some may be absorbed, but what we are assuming that everything that we are considering below the ground will be reflected back. And that's how we have to account this. This will also give you some mass of your pollutant in the air, because we are assuming it will reflect back. And that's how we have to add this term also in that situation, right? So if we have reflected plume term that we have in the Gaussian dispersion equation, that will account for the ground reflection of the plume mass, because this is below ground and we are assuming that our concentration will not go to below the ground, and that's how we are assuming that all the mass that we have, the pollutant, will reflect and will give you above the ground. And that's how we have to add this reflected plume term. So C answer is the right one. So this is something, you have plume center line, and this is your concentration that is decreasing with the distance from the plume center line, and because it should go something like that, but what we are assuming that this one we will add to this area. So here we have total plume, and this is sum of original plus reflected. So this one will also add to this part. So that's how we have to add in that kind of condition, and this is something the reflected plume. Okay, now we are moving to the derivation part. The journal transport equation for vapor phase pollutant concentration rho A1, including advection and dispersion, is deriving from, we have four options: momentum balance, energy balance, mass balance, thermodynamics equilibrium. So what we are saying is that, uh, let's say again we have a stack and we have the plume, and that plume is giving me the vapor phase pollutant, and the concentration of this vapor phase is rho A1. Okay, and this will transport with two processes. The one is advection and the another one is dispersion. And we are considering here that there is a no reaction. So if we want to calculate the concentration we will have at some point, let's say here XYZ, then this is derived from what? Yeah, this will be derived based on the mass balance. So how much mass we had initially. So we will talk about mass by time, how mass is changing with the time. Okay, and at each location we will calculate mass by time, and then we will so there will be the equation, transport equation, that we will talk about. So this is mass balance. So I just wanted to give you a brief that how we are deriving it from the mass balance. In the last week, we started with the mass balance, and what was that? We had the accumulation rate. This accumulation rate and this unit was mass by time, right? So we learned that whatever accumulation, so we started with the box model, and there is some pollutant that is coming with some flow rate, that is Q, and it is also going out with some flow rate Q, and there may be some reaction here, and that reaction may increase or decrease your pollutant. So what we learned is that accumulation rate was equal to how much mass we flow in minus flow out, plus there may be some reaction, so there is some generation, so this is G, and there may be some reaction that may decompose it or that may decay it, so there is a reaction that may remove it. So this is what we started in the last week. Okay, so from there, from this equation, how we got the Gaussian plume model, we will learn about this Gaussian plume model or the equation, and yeah, how we started with the mass balance. So I have few slide, and I think that will help you to understand what is the advection term, what is the dispersion term, then what equation at last we got, how, and based on that equation we can solve a lot of questions, right? So let's start with the derivation. I think this will take 5 or 10 minutes to make you understand what is that. So the first thing is we started with the mass balance, right? And mass balance, the unit will be mass by time, how our mass is changing with the time. So I'm starting with this one. So we already have learned that your rate of accumulation is equal to rate in minus rate out plus generation minus consumption. Okay, so and this is based on the principle of conservation of mass, and we need to derive this equation. But how we will do this, just see in the next step. Okay, so this will be your derived equation, in which just see the terminology that we are using here initially. So this is your vapor phase pollutant concentration. This is your concentration. This is ux is your wind velocity in x direction. This is dx, dy, dz. These are your dispersion coefficients. uh, this is your rho a1 by dt. This is the accumulation of pollutant. Just see this, this is the accumulation, how concentration is changing with the time. So this is accumulation, and that's why this term is this one. And then this is your advection term. We will talk about these terms in the next slide. So first what we are doing is we do have, let's a differential box. That differential box have I don't know how to draw this, but let me draw a box. So let's say this is your box, and your box have this is your zx, this is your x, and let's say this is your y. So this is your box, and box have some a dimension. So that dimension is You have del x, del y, and del z. So your volume will be the multiplication of this x, y, z, right? So you will get the volume. Okay. The second thing is you have pollutant concentration. So pollutant concentration you can get at any coordinate and at any time. So you have four dimension x, y, z, t. So what you need to calculate is mass of your pollutant per unit air volume. So this is nothing but this is the concentration, right? Mass of pollutant per unit air volume. In air, let's say in let's say 1 meter cube of air, how much mass you have of the pollutant. So this will be your concentration. So we need to calculate this using your mass balance. So again we are starting with the same thing, that we have rate in by flow, rate out by flow. Then we may have dispersion. Rate in by dispersion in the box only. In the box only, there may be by q, there is the flow rate, it is going in and going out, but there may be some dispersion, and because of the dispersion there may be some pollutant entering into the box. So this is your rate in by dispersion, and there is also rate out by the dispersion, just not by the flow rate but by the dispersion. So this is the next term. Then there may be generation and minus consumption. But here what we are assuming that there is a no reaction, so there will be no generation and there will be no consumption, and that's how this value will be 0. Okay, then these two things we can say it at the net flow transport in and out. So if we are subtracting it, then what we are getting is net flow transport. So for these two terms we are referring it net flow transport. For rate in by dispersion and rate out by dispersion, we have another term, that is net dispersive transport. Okay, so we need to calculate these two things to calculate the rate of accumulation. Okay, so we have the concentration and the volume. So if we are multiplying the concentration by volume, then this will give me the mass of your pollutant in the box. Okay, and because we need the accumulation rate in mass by time, right? How much mass is changing per time. So what we will do, we have this one, this is the mass divided by dt. Okay, so this we need to calculate how within the box how accumulation rate is changing, or what is the accumulation rate, how much mass is changing per time. We need to calculate this one. So this one is the fixed one. This is your rate of accumulation. This has been fixed. The term has been fixed. Now we need to calculate this net flow transport and net dispersive transport. Okay. And another thing that we need to learn is, if we do have the flow transport, then this is because of the velocity, wind velocity, right? So here wind velocity will have a very crucial role as comparison to the net dispersive transport. So, okay. So the first term, that is the accumulation rate, has been finalized. Now coming to the next one, that is the advection term. Coming to the advection term. So we have that box, right? We have that box. Let me... mm. So let's say this is our box. I don't know. This one is little confusing. Anyway, so we started. So this is your x direction. So this is your del x, right? So this was your x, and this is at end of this is your x plus del x. Okay, and whenever there is the advection or by the flow, there is the your pollutant is moving from x to x plus del x, then this will be with the velocity ux. Okay, and so if we are calculating this, so mass flow by advection, so initially at x it was ux rho a1 x del y del z. Okay, so and a flow out at x plus del x will be, so here we are changing it with the x plus del x. Okay, so we calculated here and here. Now we need to subtract it. Okay, so this will give you the net advection. So if we are subtracting it, we subtracted it, and this is giving you the this one. But we need to, because this is just for the one particular case, so and we are using the differential form. So for the differential form, your net advection will be, this is ux rho a1 dx, and this is del x del y del z. So, and if we are keeping constant this ux, then this will come out and your equation will be like that. So this is how we have calculated the advection term. Now we will go to the dispersion term. Okay. So dispersion can be happen in three direction. If we do have that wind, then advection will be in the x direction only, from x to x plus del x, right? But if this is the dispersion, then that can happen in the three direction. And this is in x direction, y direction, and z direction. So we need to calculate the mass flux due to dispersion in all these directions, right? So here we are talking about the flux. Just keep in mind, so the flux in at x, so this is right now the flux that we are defining are nax, nay, and naz. So this is flux in at x, so this one, and del y del z. At out, so this will be changing, and that's how we will calculate net x dispersion. So we will subtract it, so this will give you the net dispersion in the x direction, but we need to calculate it for the y, and we need to calculate it for the z direction also. So if we are calculating this for the y direction, so this is something like for the y direction, and this is for the z direction. So total dispersion will be, if we are summing this up everything, and this will give you the another term for the dispersion. So just keep in mind, in advection we had velocity term, right? But here we do not have that velocity term, we do have that flux, right? We have the dispersion flux that we are talking about right now. Okay, so another thing that what we are doing is, we have Fick law. I will talk about this Fick law in the next slide, because I have one or two MCQ question on this Fick law also. So in the Fick law, we are forming a dispersive flux like this. Okay, so now what we are doing is, we are adding everything. So this is for x, y, z, and this is what we will get for the dispersive flux. I think you need pen and paper to calculate it. I will share this slide, you can have this. Okay, now we will write our full balance equation. This was your accumulation rate, this was your accumulation rate, this was your advection term, that is the your flow by flow, net flow, where we have that velocity term, and then these are giving you the dispersive term, right? Then we will divide everything by volume, and this is how what we will get. So this is your final model. So most of the models start from this equation only. Okay, then if we are keeping our velocity and dispersion coefficient constant, then these things will come out of this partial differential equations, and that's how this is giving you the final thing. So this is your equation that you get. Then if we do have steady state means this has to be zero, this has to be zero, and if we are moving this into the right hand side, so this will give you the another equation for the steady one. And the another manipulation that we can do is that our dispersion in the x direction is very less as comparison to moving with some velocities, and then we can also ignore this, we can also neglect this. So after all, if we do have steady state, and if we are assuming that our dispersion is very less in the y direction as comparison to the movement due to advection, then this will be ignored. So we will have just three terms, this one and this one. Okay, so these are based on what condition, or what uh, how we are simplifying it. Okay, as I told you, if we do have steady state simplification, then we are putting it as zero, and this is how this will be our equation. And the next one is, okay, so the main crux that we are getting from it is that we have advection. So pollutant are carried by wind. So this is our advection term. This is your wind velocity, concentration changing with y distance. Okay, so this is your advection. Then there is a dispersion because we are neglecting the dispersion in x direction, because what we are seeing is that there is just the movement of pollutant just because of the wind. So we have just two terms here, a spread in y direction and x direction due to the dispersion, and we already have calculated this. And you have pollutant concentration change with the time. So this is rho a1 by dt. So these are the things that we learned, and now based on these things we have a lot of mcq question, and I think this derivation will help you to give me the answer for these questions. Okay, in the derivation of atmospheric dispersion equation, dispersion flux is modeled using, we have four points here: Newton law of viscosity, Darcy law, Stokes law, and Fick's law. Yeah, so D answer is the right one. So we already have learned that whenever we are modeling the dispersion flux, then we have to follow the Fick's law. But as I told you, I will discuss this Fick's law in this question only. So what it is that, let me show you. So in the Fick's law, that state that diffusive flux of the species is directly proportional to the negative gradient of the concentration, high concentration to low concentration. So if there is a high concentration and the low concentration, then your diffusion will be from high concentration to the low concentration. I know this is a well-known thing, but this was given by the Fick law. Okay, and this was just the term that he has given. So this is ja, this is diffusive flux of species a, and this is diffusion coefficient, and concentration of species a, direction of diffusion. So and this is d, so this is giving you the gradient, right? So how the concentration is changing higher to lower and with the distance. So this is giving you the gradient of the concentration. So if you have high concentration, then your dispersion will be more to the lower concentration, from higher to the lower, and that has been given by Fick law. So this is just the expansion of this Fick's law, because your dispersion can be happen in the three direction, x, y, and z, and that's how we can write three terms here, and then we are combining it, we are doing the summation of this. Okay, so we already have derived this one, right? There is a no problem, I think, with this term. And now this one, this term, so this term represent what? Turbulent diffusion, convective transport, chemical reaction, or molecular absorption. We have already learned about these terms, right? So what this term represent? So B answer is the right one, because this is we talked about, right? So whenever there is a transport of your pollutant, that can be due to wind, or by flow, or by dispersion, right? So this term is showing you by the flow, transport by the flow. And so this will be the convective transport, and these three are showing you the dispersive or the dispersion terms in the x and y and z direction. Okay. The next very much important thing that we need to discuss is Lagrangian and Eulerian concept of the model. So, if we do have Lagrangian dispersion model that will track, we have four options: fixed spatial grid, fluid parcel movement, average wind field, and reaction rate variation. So we have two type of two in two way we can see the transport. The one is Lagrangian and another one is Eulerian. Yeah, so B answer is the right one. That is the fluid parcel movement. But you have to understand first what do you mean by Lagrangian and what is Eulerian. So we have two way by which we can have that equation. So yeah, so whenever your reference is fixed, whenever you have fixed point, then that means you are talking about the Eulerian. But when your reference is also moving, then we are considering, then this is the Lagrangian model. So this is moving with the fluid. And this you can see by this thing also. So initially there was the this is the control volume that is fixed in the space. So this is your Eulerian flow model. But because we know that your pollutant, the box is also moving, right? So if your reference is also moving, so differential volume control convective with the flow, so this is moving. So if it is a moving and then we are calculating this concentration and change in the mass per time, then this will be under Lagrangian flow model. I also have given a lot of differences between this. So in the Eulerian approach, we observe pollutant concentration at fixed location in the space, but here we are following the individual pollutant particle or air parcel as they move. Here we do have very fixed reference frame, that is XYZ, but here we are moving our parcel and particle, and that's how we have moving reference. Then we are tracking here the concentration, but here we have to track the position and the trajectory of the particle also, and that's how we are having this Gaussian flow model. Then these are the mathematical terms that we can use. And interpretation is we are measuring the concentration at receptor or the grid point, but here in Lagrangian approach, we are tracking where the pollutant goes over time. So that's how in fluid dynamics and how our pollutant is moving in the space, we are mostly following this Lagrangian approach. Okay. So the next question is, in atmospheric plume modeling, the Gaussian plume model assumes unsteady emission, instantaneous source release, steady state condition, chemical equilibrium. So we talked about the Gaussian plume model, right? But in the Gaussian plume model, we do have a lot of conditions that we have to follow to simplify the equation that we learned, that we derive. So what condition that we have to apply to make it simplify? Yeah, so C answer is the right one. That is steady state condition. So as I told you, this is, let's say again, your chimney, and this is the center line, and there is because it is following the Gaussian distribution, so that's why this is Gaussian flow model. But there are a lot of conditions that we are following. The first condition is that the wind velocity that we are having is constant. It is not changing. Whatever wind velocity that we have here will be here also. This is not in the real case, but in Gaussian flow model, we have to simplify with a lot of assumptions. So the first thing that we are talking about is that wind velocity is constant throughout. This is your first assumption. The second assumption that we are having is that there is no any reaction. There is no any reaction, just there is dispersion, and there is just dispersion, and it is flowing with the advection. So this is your second condition. The third condition that you are having is because there is a no reaction, it means there is no any accumulation rate. So your, if your accumulation rate is equal to 0, then it means it is following the steady state condition. Okay, because there is a no accumulation, there is a no reaction. So these are few conditions that we have to follow for Gaussian flow model to simplify it. Okay, so C answer is the right one. Which assumption allows the time derivative term to be neglected in dispersive modeling? High turbulence intensity, steady emission rate and constant meteorology, zero wind velocity, large particle size. As I told you, we have dispersion, right? Dispersion in X, dispersion in Y, and dispersion in Z. But whenever when we were deriving, then I told you that this dispersion in the X direction can be neglected, right? This can be neglected. We are just keeping the dispersion in the Y and dispersion in the X. Sorry, dispersion in the Z. We are neglecting the dispersion in the X direction. How we can neglect it? What are the conditions? Why we are neglecting this? So the right answer is B, that is the steady emission rate and constant metrology. If we do have constant metrology, then what? In the Gaussian, we talked about it, right? That we have a constant velocity. If we do have that constant velocity, it means every time there is the transport of your pollutant due to that velocity, particular velocity, it means that whatever the transport you have is mostly due to that wind thing, as comparison to the dispersion in the Y direction, because wind is moving in sorry, in the X direction, sorry, in the X direction. If the stack plume is moving, then there may be spread due to the dispersion in Y and X direction. But because our wind velocity is also moving in the X direction, then what we are considering, because we do have constant meteorology, we have constant velocity, and that's how dispersion will be negligible as comparison to the transport of your concentration or the mass due to velocity. Okay, so I think I have explanation for this also. So this is something like that. So in the steady state assumption, what we are having is that emission rate from the source is also constant. Whatever rate it is coming from out of the chimney, that is the constant. If this is the constant, and if our meteorological condition is also constant, it means your concentration field is not changing with time. So this is your steady state. We already have learned about this steady state, right? And in that condition, okay, I didn't. Okay, I think in next I have. I think, yeah, this one is giving me the right explanation. So, yeah. So this is something that if you have wind velocity or wind speed that is, let's say, 1 to 10 meter per second, and your dispersion coefficient is something like that. But we know that in the x direction, if our wind is moving, then your advection is much stronger than the spreading caused by the diffusion. So here what we are saying that this term is negligible as comparison to this one. But what are the condition? If your emission rate is constant and your meteorology condition is also constant, so in that way you can come up with that B answer being the right one. Okay. The next question is, in the Gaussian plume model, you have four key input. What are these four key input that you have? Q, Ux, H, sigma Y, sigma Z, Q, Uy, T, dx, QPH, sigma X, UXH, rho K. What are the key input that we need to have to calculate the concentration of your pollutant at any location XYZ with XYZ coordinate? So what are the four key input that you need to have under this Gaussian plume model? What are four input that we need? If you want to, let's say that this is the stack and this is giving you the concentration here. Here I have receptor and this is XYZ. So if I want to calculate the concentration here at the receptor, then what are the four key input that I should have to follow this Gaussian plume model? Yeah. So A answer is the right one. So for that, the important things that we need to have is the your emission rate, that is Q. So how much emission we have out of this chimney. So this is Q divide by 2 pi. Then we have wind velocity. So this is your Ux, right? And then there is a dispersion in the y direction and dispersion in the x direction. And then there is the exponential terms that we have, which are related to your y, sorry, x, sorry, this h, and this h is your effective stack height, right? So these are the four or five things that we must have. We must know how your pollutant is spreading. We should know what is the emission rate. We should know what is the wind speed. We should know what is the height of your chimney. Then only we can tell what will be the concentration that we will have at particular location. So these are four or five terms that we should have to calculate the concentration. Okay. So for the ground level source, if our source have ground level source, a height term become h is equal to 1, h is equal to sigma z, h is equal to u, h is equal to 0. So what I'm saying is that we do have ground level source, so we do not have chimney, right? So it is something that we are burning wood here. We are burning wood here. And then you need you have the receptor here. So in that case, obviously your source height, that is h, is nothing but because this is the ground level, so uh, your h will be equal to 0. So D answer is the right one. Okay, if your pollutant emission rate, that is Q, is equal to 20 gram per second, wind speed is U, that is equal to 5 meter per second. Cross sectional plume area at a section A is equal to 10 meters square. And then the average concentration based on simple mass conservation, that is Q is equal to UAC, is 0.2, 0.4, 2.5, 10 gram meter cube. So this is just very simple thing. You have emission rate, you have wind speed, you have area. So there is no any advection or nothing. Just we are following very simple mass conservation, that is Q is equal to UAC. And based on this particular equation only, you need to calculate the average concentration. So average concentration will be C will be equal to Q by UA, right? Q is 20 here. U is 5 multiplied by 10. This we are crossing. So this is 2 by 5, which will be equal to 0.4. Right? So this is very simple. If you have emission rate, if you have wind velocity, if you have area, then you can calculate the concentration based on very simple mass concentration. So the B answer is the right one. Okay, so the next question is, if you have U is equal to 4 meter per second, and you have partial differential equation that you have is dc by dx is equal to 0.03 gram per meter raised to power 4, then you have advection term. This advection term, this is this one. This will be equal to what? I think simple multiplication, because everything is given in the same form only. And we know that advection term will have the wind velocity. If you have wind velocity 5 meter per second, and yeah, so this is how we need to just do the multiplication, and this multiplication will give you the value. So this will be 4 multiplied by 0.03. So this will be equal to 0.12. So this is how you can calculate, but this is very simple question actually I put, but sometime it is something that you need to do the derivations. You need to put the values in concentration and the distance, and then you have to solve this differential equation. So that will be little complex for you. So that's why I'm just giving you the value of this partial differential equations already, and that's how you can calculate this. Okay, so if we are using the limit when integrating plume mass across the cross section are usually, for the y this is 0 to infinity, for the z this is minus infinity to plus infinity, for the y minus infinity to plus infinity, for the z minus infinity to plus infinity. For y, this is minus infinity to plus infinity. For z, this is 0 to infinity. For y, this is 0 to infinity. And for z, this is 0 to infinity. Again, I'm drawing the same thing. If you have that chimney, you have plume. So this is something like this. And so your limit, so let's say this is your spread in the y, these are spread on your y, these are spread on your x, sorry, z, these are spread on your z, and this is your x direction. Just give me a minute. What happened? Yeah, so no, D answer is not the right one. Why this is not the right one? Because in the horizontal direction this can be infinity, the spread can be infinity, but in the in the vertical direction we will have the ground, so it will be from 0 to any height, so this will be 0 to infinity. But in horizontal direction the plume may disperse in from infinity, minus infinity to plus infinity. So here, because this is horizontal, this horizontal can be anything, right? So this is minus infinity to, this can be go up to plus infinity. But if we are talking about this zx, sorry, the sigma x, sigma z, then this can be up to infinity. The up can be up to infinity, but this portion, this spread will be till zero, right? Because otherwise it will be reflected, and then it can't go to the minus sigma, minus sigma x, sorry, z. So that's how, for the y, for the horizontal spread, it can be infinity to infinity, but for the vertical spread, it will be from 0 to plus infinity. So that's how C answer should be the right one, right? Okay. The next question is, we already have derived this, right? In the derivation of simplified Gaussian plume equation, which term is neglected because advection in x dominates over longitudinal spreading? A, B, C, D. Which term we can neglect? So what we learned from this derivation is that we have accumulation rate, and this accumulation rate was Vc upon dt by volume. So this is into volume. So this is your accumulation term, and then you had due to advection and due to your dispersion, right? And this is your advection term, plus you have dispersion, dispersion in x, dispersion in y direction, dispersion in z direction, right? So actually this advection will be always there. We can't remove this. This C is not the right answer. The right answer will be D, because uh, this advection is giving you the transport in the x direction, right? In the x direction, if there is a flow, then this flow will be more than uh, the movement due to dispersion in the x direction. So this term, the dispersive term that is representing the x direction, will be removed, will be neglected. But this advective term, because the velocity is very stronger than the dispersion, right? And if your velocity is in the x direction, then the dispersion that we have in the x direction we can neglect, because we have very strong velocity in the x direction. So what we can remove is just the dispersion in x direction, because we do have the strong velocity effect, right? And that's how the dispersion in x will be just removed. So this will be maintained. Yeah, this will be maintained. Y and z dispersion will also be maintained, because the velocity is in just the x direction. So yeah, this one we can neglect. So yeah, uh, D answer should be the right one. In simplified steady state advection dispersion equation becomes, this is like initially we had five terms, right? The first term is the accumulation rate, the second term was the so accumulation rate will be equal to your advection term plus your dispersion term, and your dispersion has three terms, x, y, z. So if you have steady state, so in that steady state, out of these four terms, we sorry, out of these five terms that we had, so what will be remaining one? So you had accumulation rate initially. After that, you had the advection term, the term number two, and then we had three um, dispersion term, x, y, z. But if we do have very steady state condition, that five terms will be summarized into what? Yeah, the answer is right. You rightly said B. So how it is B? Because this delta C by delta T, we are keeping it zero, right? Because there is a no accumulation, because it is the steady state. So the first term is has been zero, and we also ignore, if it is the steady state, then we can ignore our dispersion in the y direction, right? So we are also removing that. So we will have just three terms, and these three terms will be, so your advection, that is u and u delta c by delta x will be equal to your dispersion flux in y and in z direction. So this will be your final that you will have. So whenever your equation is saying that you have the steady state, then you need to remove your two terms, and you just need to focus on your three terms that you have in the option B. Okay, in the Gaussian plume framework, the x-axis is defined along the geographic north, stack height, wind direction, crosswind direction. We already have talked about this a lot. If this is the x direction, then how we are defining that this is the x direction? No, x direction is giving you the wind direction. X direction is the wind direction. Crosswind direction is the y direction, right? Crosswind is the y direction. Stack height is the x direction. Geographic north is nothing. So just see now, if there is a stack, and stack is giving you some plume, and the wind velocity is giving you plume to move to the x-axis, and there is a receptor, it means wherever this is wind is moving, this is giving you the x direction always. Okay, and if there is a spread, the crosswind, this crosswind is giving you the y-axis, and your stack is giving you the x-axis. So C answer is the right one. Okay. For the advection term, uh, the advection term that we have. In the advection term, if wind velocity is given, that is 5 meter per second, and your pollutant concentration gradient is also giving, that is 0.02 kg per meter raised to power 4, then your advection term magnitude will be what? Again, I have given everything ready made, right? You are not I'm not giving you to derive or to solve your partial differential equation. I'm just solving it, and I'm giving the value for this pollutant concentration gradient. So for the advection term magnitude, you just need to multiply, right? So yeah, so A answer is the right one, because you are just multiplying. Okay. So, as I told you, we have five terms. Initially, we have five terms in the Gaussian, in this equation, mass balance equation, and this last term is representing what? Turbulent diffusion, convective transport, chemical reaction, molecular absorption. Yeah, so this is because it has the velocity term, then this is giving me the convective transport. So yes, B answer is the right one. In simplified steady state plume equation require boundary condition in x direction, y direction, z direction, xyz direction. So we have box, right? We have box, and within box we are calculating the concentration. Now for the box, you know that the dispersion can be in x direction, dispersion can be in y direction, and dispersion can be in z direction. Okay, so dispersion can be in any of the direction. Okay, and then there will be the advection will be in the x direction. So we need to tell at the top of this each faces, either it is x face or y face or z face, we have to give some value. So these are something, the boundary condition that we have. At the boundary, we are having the dispersion, right? Yeah, so we need boundary condition in every direction x y z, then only we can tell the dispersion. Okay, otherwise we will not able to tell, we will not able to solve that partial differential equation for the dispersion term for the y x and z term. So we need that boundary condition to solve it. We already have talked about this, I don't need to. Yeah, in Gaussian plume model, the maximum concentration at the given x generally occur on the ground, plume center line, upwind side, plume edge, where you will get the maximum concentration. Yeah, so you will get maximum concentration at plume center line. It is just like it is just like that your normal distribution you have. So I'm just giving you the one example. If you are calculating, if you are having the height of 50 student, right, height of the student, 50 student, and then you are calculating its frequency. Okay, the height frequency, then there will be some height. So for example, your height, the 50 student height is from let's say 4 foot, 4 feet to let's say 7 feet. Okay, but few people will have that height of 5 feet and 7 feet, but most of the people will have the height of 5.5 feet something, right? So at the peak, at the and so this will be at the center. Okay, at the center you will have the high number of students that will have that particular height. So like, so this is following your normal distribution. Like this only, your plume is also have that normal distribution. At the center you will have the highest concentration. At the tail you will have very few student and very few concentration that you will have, but high concentration will be at the center. So this will be at the plume center line. So B answer is the right one. Okay, in the Gaussian equation, we have sigma y and sigma x that represent what? Reaction coefficient, wind fluctuation, crosswind and vertical spread parameter, stack diameter. So these are the spread, right? Yeah, the spread in the y direction and spread in the vertical direction, horizontal spread and the vertical spread of your concentration. So this is the crosswind and vertical spread parameter. So yeah, C answer is the right one. uh, then we have Gaussian plume model that use the Lagrangian style interpretation. We talked about Lagrangian. So the key reason is what? Earth rotation is neglected. The plume is followed relative to its own motion and wind direction. Pressure is constant everywhere. Dispersion occur only in x direction. As I told you, Lagrangian is following. Your reference point is also not stable. It is moving. So there is a motion. Yeah. So that's how B answer is the right one. Okay, the next question is wind speed used in the Gaussian model should ideally be measured at what? Ground level, mixing height, stack height, and the sea level. So, because in the advective term, we have the wind speed, but at what location we should measure this wind speed? This wind speed should be measured at the stack height, because at the stack height only there is a center line, right? And the plume is spreading from the center line only, and this center line is related to your stack height, right? So, and most of your concentration is the center line, so your wind speed is should be measured at the stack height only. So C answer is the right one. You know that wind speed generally increases with the height. Why? Air density increase upward, ground friction reduce near surface velocity, pressure is constant aloft, and turbulence disappear near the ground. Why there is always high wind velocity at altitude with the height? Why this is the condition? Because there is a friction in the ground, and that friction will resist the wind speed, will reduce the wind speed. And that's how whenever there is a building or there is a ground, there will be the friction. So that's how the wind speed will be reduced near to the ground. But if we will cross that ground and building, the wind speed will be higher. Okay. And so that's how your wind speed increases in the height, because there is a low wind speed the ground because of that ground friction. You know about the windrows, right? Windrows will give you what? Windrows is the graphical representation. Yes, that graphical representation that is not only giving you the wind speed but is also giving you the direction. So yeah, B answer is the right one. In meteorology, if we are saying that this is the northerly wind, so it means what? Going toward north, coming from north, circulating around north, measured only in northern hemisphere. So this is because such kind of term is very important in the Gaussian plume model, because otherwise otherwise advection term will be completely opposite. So this is, yeah, coming from the north, then this will be the northerly north. Okay, the very important concept that we talked about that spread, right? We talked about spread in the horizontal direction and in the vertical direction. But how we can calculate that spread? To calculate that spread, we must know the wind speed, whatever we have. We also should know the stability of your atmosphere, either your atmosphere is stable or not, because whenever there is instability in the atmosphere, the spread will be more, right? So that's how it will disperse more. So to calculate your dispersion in horizontal and in vertical direction, you need to know the stability class, you need to know the wind speed. And yeah, so to calculate this spread, Pascal Gifford gave the stability classification. Okay. And this classification is mainly a simplified way to estimate. So, and there is these two scientists gave the stability class, and based on stability class they also gave some spread value based on some graph. Okay. So yeah, so this stability class we can use to estimate the spread in the horizontal and the vertical direction. So C answer is the right one. So these are stability classes that has been given by Gifford. So A is extremely unstable, B moderately unstable, C weakly unstable, D is neutral, E is weakly unstable. And we already have learned how our atmosphere will be stable or unstable based on your lapse rate, dry adiabatic lapse rate and environment lapse rate, right? We talked about this, right? Then based on these classes, it talked about that whenever your wind surface speed will be less than 2, and if it is a daytime insolation is, let's say, strong, then you will have stability class A. So likewise, if you are talking about your atmosphere in the daytime or nighttime and what is the wind speed, based on that they categorized the stability classes from A to F. Okay. And then for each of this stability class they gave the spread value. So these are, so can you see A, B, C, D, E, F? So for each classes and from distance from the source. So if we are going more from the source, dispersion will be more, right? So it give you the spread. In the A part, this is spread in the horizontal direction, and uh, in the B graph you have dispersion in the vertical direction, and for each different class. So this is how we can calculate the spread. Under very unstable atmospheric condition, the vertical dispersion parameter sigma z is generally small, zero, larger, independent of distance. If you have very unstable atmospheric condition, then your vertical dispersion will be what? More, less, zero, and it is independent of distance. We already have talked about this, right? If we have unstable atmosphere, unstable means the wind will flow, wind will disperse the things very rapidly. So that's how your vertical dispersion will be larger if you have unstable condition. Yeah. So C answer is the right one. If you have unstable condition, if you have stable condition, then your plume spreading in the vertical direction is strong, weak, infinite, equal to horizontal spreading. If there is a stable condition, means there is a no any mixing in the air. So if there is a no any mixing in the air, then the plume spreading, what will be the case for the plume spreading in such case? That if there is a no mixing, the atmospheric condition is very stable, so spreading will be less, right? Spreading will be weak. So B answer is the right one. Okay, we talked about this classes, right? That Pascal Gifford gave. So the class D represent what? Extremely unstable, neutral, moderately stable, very stable. Yeah. So this is B, that is neutral. We talked about this, right? These were our classes A, B, C, D, E, F. For each classes, there is a dispersion in the x and y direction that we have seen using that graph. If you have a very clear night with low wind speed, the atmosphere is most likely to be unstable, neutral, stable, convective only. If you have very clear night and low wind speed, then your atmosphere will be what? So wind speed has very much strong relation with the stability. If you have more wind speed, then there will be more mixing, right? If you have low wind speed, there will be less mixing. If this is less mixing, then your atmospheric condition is very stable. But if your wind velocity is very high, then there is a lot of mixing, a lot of turbulence will happen, and that's how everything will be mixed up. So your atmosphere will be unstable, and unstable is very good condition for the dispersion. So if you have clear night with low wind speed, then it means your atmosphere is stable, because there is a no any mixing. The layer each layer is not mixing with each other, because wind speed is not allowing it to mix to each other. We have term that is effective stack height that we can use in Gaussian dispersion. So this effective stack height is at what? Yeah, so this is the physical stack height plus the rise we have. Plume will rise, right? Why the plume will rise? I think next question I have. So yeah, so effective stack height is your real stack height that we have, and the plume is also rise. So if we are adding it, then we will have the effective stack height. Okay, the next question is, why the plume rise? Why the plume rise? Due to diffusion and reaction, stack exit velocity and buoyancy, crosswind turbulence, or ground reflection. your plume is coming out of the chimney, but it will first go straight, little straight, and then it will follow some direction. So why it is rising first, why it is rising vertical first? What are the reason for that? This is yeah, this is all about the momentum, all about the inertia. Whenever you have high velocity with which the plume is coming, then your velocity is very high. If it is a straight coming out, then it will go initially straight. So this is your exit state velocity. And the second thing is buoyancy that we get, upthrust that we will get, and that's how it will first rise and then it will disperse, right? So that's how there is a plume rise due to velocity and the buoyancy. Okay, this is a very simple question, and then we will end here the session. So if your stack physical height is 60 and plume rise is 25, then what should be your effective stack height? Yeah, this is plus, right? You will add it. So this will be 85. Few questions we are left with. I think based on, we didn't talk about fugitive term, and the another one is this is all about when you have leakage in your chimney, or let's say if your height is the chimney height is very less, then what will happen? So these two scenario that we need to discuss, I think we will discuss in the next class. So till now, uh, read more, and yeah, if you have any query you can just let me know. My mail id, that is jyoti21 at the rate iiserb.ac.in. And yeah, happy reading, and have a good dinner and good night. If you have any query you can just let me know, otherwise you can leave the call.